Welcome to Section 3.3 of the Intermediate Algebra Online Video Lecture Series by Dr. Scott Franklin. In this section, we're going to start talking about systems of linear equations in three variables. That's right, we're kicking it up a notch. We're going to go up to the next level. We've solved 2x2 systems using three techniques. We're going to now solve 3x3 systems, and we're going to propose just one technique for how we would solve a system of equations that involve three variables. What we run into is as you increase the number of variables, the problem gets harder and harder and harder and a lot more complicated to solve. In fact, after you move beyond 3x3 systems, you really need to introduce a new type of technique. And there's a whole field of mathematics called linear algebra, which is all about solving larger and larger systems and properties that those systems have. Now we're going to stop at three variables, but let me show you the techniques for how we solve a system of equations that has three variables and three unknowns. In this section, we're going to cover just two essential concepts. One, we're going to learn how to verify that a solution is in fact a solution of a system of linear equations in three variables. And secondly, we're going to learn how to solve systems that involve linear equations of three variables. Say we're given a linear system like this example right here. We've got a 3x3 system. What you have now are equations that have three variables. They're linear in the sense that every variable appears at most once. It's to the first power. You don't have any squares, you don't have any square roots, and no two variables are multiplied together. That's what we're going to mean by linear from this point on. Okay. Now what we want to do is verify that this system has the solution 2, -1, 3. Now I've called this an ordered triple instead of an ordered pair because there are three numbers. But the order is significant. And just like before, the first one, just like in an ordered pair, would represent the x variable. The second component of that ordered triple represents the y variable. But now we have a third variable, and so the last number represents that variable, which makes sense if we're only going to consider three variables to consider x, y, and z. Now in order for this ordered triple to be a solution to the system, it has to satisfy all three equations simultaneously. So to verify that it is a solution, we're going to plug in x equals 2, y equals -1, z equals 3 into each of these three equations and confirm that they are true. Okay, so I'm going to call this equation 1, this equation 2, and this equation 3. So if I were to check equation 1, plugging in x equals 2, I would have 2, and y is equal to -1, and z is equal to 3. The question is, does that equal 4? Okay, well 2 plus a -1 is 1. 1 plus 3 is 4. That equals 4, so yes. So far, so good. First equation is satisfied. But in order to be a solution to the system, it has to satisfy all three. So check equation 2. Plugging in 2 for x. Okay, again, I'm plugging in right here, equation 2. I'm going to plug in a -1 for y, so -2 times a -1 for y, minus what z is 3, so -3. Question mark, does that equal 1? Okay, well, we multiply first. -2 times -1 is going to be +2. 2 plus 2 is 4. 4 minus 3 is 1. That does equal 1, so equation 2 is satisfied. Equation 3 I'll check in the same way. Substituting in for x is a 2, and for y is a -1. Notice there's a minus here, and then y is -1, so I'll have minus a -1 plus, actually -2 times 3. Question, does that equal -1? So that's 4 minus a minus is +1 minus 6. 4 plus 1 is 5. 5 minus 6 is -1. That does equal -1. So it checks. Yes, it is a solution. Now, we want to be able to solve linear systems. So here are some steps that I recommend for a fairly reliable way of well, it's reliable, a fairly simple way to solve linear systems. You wouldn't want an unreliable method to come through in your algebra class, so this is going to give us the answer. But we're going to do it in the following way, and I think this is probably the simplest way for us to get the solution. What I suggest that we do is, number one, reduce the system from 3 by 3, that is 3 equations, 3 unknowns, to 2 equations with 2 unknowns. This is usually accomplished by taking 2 different pairs of equations and using the addition method to eliminate the same variable from both pairs. If you do that, you'll have 2 different equations in 2 variables. Okay? Once you've gone from a 3 by 3 down to a 2 by 2, we now go back to what we did in the previous 2 sections and solve the resulting system of 2 equations using 2 unknowns, either by graphing, substitution, or addition. I recommend either substitution or addition at that point. Okay, once we get that solution, we'll have 2 of the variables, right? We will now solve those 2 equations. So how do we find the third variable? Well, we use back substitution. So we back substitute the value of the variable found in step 2 in either the 2 equations to find the second variable. Then we use the values of the 2 variables from steps 2 and 3 to find the value of the third variable, okay, by going back one more step. Okay, so we've reduced the system to a 2 by 2. We go through the process of solving it and back substitute to find the remaining variables. An example will help clarify that if that's a little bit confusing, but you'll see what I mean. Once we get the answer, we can always go back and check the solution in each of the original equations, verifying that it is in fact the solution, as we did on the first page of notes in this section. Consider the following system. X plus y plus z is equal to 4, x minus 2y minus z is equal to 1, and 2x minus y minus 2z is equal to negative 1. Now, the best suggestion I have, and of course you've got a lot of choices here with this, but here's the suggestion I have, is find one of the variables that has a coefficient of 1 or negative 1. And we're going to use that equation to eliminate that variable. Okay, so let's say, for example, look at the first 2 equations here. It's actually pretty easy here. If you look at equation 1 and equation 2, right, calling this 1, calling this 2, let's call this 3. If I add those together, what happens to the z? Immediately the z drops out. Right? So if I took 1 plus 2, I get x plus y plus z is equal to 4. That's equation 1, plus equation 2, x minus 2y minus z equals 1. Add those together, I will eliminate the z variable. Okay? So I've paired these first 2 up and have eliminated the z variable. X plus y equals, well, actually add this up, I get 2x minus 2 plus 1 is minus y is equal to 5. Now what I want to do is somehow create a second pair, either the first and the last or the second and the last, and eliminate the same variable. Okay? And I think if I did the first one and the last one, I can still eliminate the z variable, right, by multiplying the first equation by 2. Now here's the thing. You're going to take 2 different pairs. You want to eliminate the same variable both times. And it's using this multiplication by a non-zero number times one of the equations to add it to the other to get that variable to cancel out. In this case, I'm going to take 2 times equation 1 and add that to equation 3. Right? 2 times this added to this should get rid of my z again. So what's 2 times equation 1? Take 2 times everything in equation 1. I'd get 2x plus 2y plus 2z is equal to 8. Be sure you do it on both sides. And then just take equation 3, 2x minus y minus 2z equals negative 1. If you add that up, again, the z's cancel out, which is what we want. Okay, 2x plus 2x is 4x. 2y minus y is plus y is equal to 8 minus 1, which is 7. By doing this twice, I've got now 2 equations. 2x minus y is equal to 5, and 4x plus y is equal to 7. I've got a 2 by 2 system. Now I can go back in any technique I want from 3.1 and solve this system. Now the easiest way I see is by addition, because if I add these together, the y values will cancel out, right? If I add these, right, if I say I call this equation 1 prime and 2 prime, just put a little apostrophe up there and call it a prime. I'm going to take 1 prime and add it to 2 prime and see what I get. Right? I'm going to take 2x minus y equals 5 and 4x plus y is equal to 7 and add them up. That gives me 6x, the y's cancel, equals 12. Okay? Now to get the x solved for, divide both sides by 6, I end up with x is equal to 2. Now I have found now one of my variables. Now how do I find the others? Well, I suggest we do the following. Let's substitute x equal 2 back into one of these two. Okay? Let's say into 1 prime, into this equation right here. And you don't have to label these the same way I have. That's a way of me referring back to equations that I have in my problem. So 2 times 2 minus y is equal to 5. That gives me 4 minus y is equal to 5. If I subtract 4 from both sides, I get minus y is equal to 1. Dividing off the negative 1 gives me y is equal to negative 1. Okay, so now I've got an x and I've got a y. How do I get the z? Well, x, y, if I plug that into, say, one of these three equations right here, I'll have only z as unknown. So I'm going to substitute back into, say, equation 1. X equals 2 and y equals negative 1 into equation 1. That gives me 2 plus a minus 1 plus z is equal to 4. 2 plus minus 1 is 1. So 1 plus z equals 4. Subtract 1 from both sides. I get z is equal to 3. So my solution is x equals 2, y equals negative 1, and z equals 3. Which, by the way, this was the same problem we had on the first page. So you can see now where the solution came from. And if you want to see how we check it, go back to page 1 and see how we verified that that was in fact the solution. But that's the solution to this system. This order triple satisfies all three of these equations simultaneously. Alright, here we've got another problem. 3x plus y plus 2z is equal to 5. X minus 3y plus 3z is equal to 2. And 2x plus 3y minus z is equal to 1. Again, my suggestion, of course, the technique that I gave you says we need two different pairs. But how do we decide which pair we want to use? My best suggestion to you is to find, like I said, one of the variables in this problem that has a coefficient of 1 or negative 1. I could either use this x here, or I could use this z down here. And what I mean is, let's include that equation twice in each pair. Okay? So I'm going to use this one, right? What I'm going to do, of course, calling this equation 1, 2, and 3, I'm going to start with this pair. Because I can get rid of this z pretty easily in both of these by multiplying this one by 2. Right? And leave this one alone. So take equation 1 plus 2 times equation 3, right? Multiplying this by a 2. Add them together, will cancel out. So just rewrite that. Equation 1 is 3x plus y plus 2z is equal to 5. Now take 2 times the last equation. 2 times 2x is 4x. 2 times 3y is 6y. 2 times minus z is minus 2z. And 2 times 1 is 2. Add those together. I'll get 7x plus 7y, the z's are gone, and that equals 7. Okay? Now include this last one again in the same, but try the other equation. Now what can I do to get rid of the z's this time? Again, I got to get rid of the same variable, so that's what I'm going to do. I can take this times 3 now, right? I can take this equation, equation 2, add it to 3 times equation 3. Right? That's how I get rid of this z. Because that's a 3z, I want this to be a minus 3z. So that means equation 2 is x minus 3y plus 3z is equal to 2. Now multiply the last equation by 3. That gives me 6x plus 9y, 3y times 3 is 9, minus 3z is equal to 1 times 3 is 3. Now add them up and see what you get. 6x plus x is 7x. 9y minus 3y is plus 6y. The z's are gone. 2 plus 3 is 5. Now there's what my new system looks like. I have 7x plus 7y equals 7. I have 7x plus 6y is equal to 5. So I would call this equation 1 prime and this equation 2 prime. Now, what can I do to simplify this or to solve this system? Well, again, I can choose any of my techniques. I can use graphing. That's not so good. I could do substitution, or I could do linear addition. I'm going to do addition again because it's pretty easy to get these to cancel. Right? What if I just took the second one times a minus 1? What if I took equation 1 prime plus a minus 1 times that second equation? Take this minus this. Right? That is 7x plus 7y equals 7. And take minus 7x, just multiplying this by negative, minus 6y equals negative 5. And add that up. The 7x's subtract out. 7y minus 6y is just y. And 7 minus 5 is 2. So I've got y equals 2. Alright, I'm part of the way there. Now let's substitute. Let's substitute y equals 2 into equation 1 prime. Let's put 2 back in here. So I have 7x plus 7 times 2 is equal to 7. That is 7x plus 14 equals 7. Subtract the 14. I have 7x is equal to negative 7. Divide off the 7. X is equal to negative 1. Now let's substitute y equals 2 and x equals negative 1 back into one of the original equations. So let's say we do it back in equation 1. That gives me 3 times minus 1, x is minus 1, plus 2 for y, plus 2z equals 5. So that's minus 3 plus 2 plus 2z is equal to 5. So minus 3 plus 2 is minus 1 plus 2z equals 5. Sorry for cramming this in, but I can do this. Add 1 to both sides. I get 2z is equal to 6. Divide both sides by 2. Z is 3. So altogether, my solution looks like this. It's x is negative 1, y is 2, and z is 3. And you can verify by plugging that back into the original equations, and it does check that that is the solution. I'll save the time on the video by not doing the checking step, but that's correct. Okay? Alright, so that's the end of how we solve 3 by 3. I could do more examples, but they're all going to be just like this. I encourage you to watch the videos on the online homework as necessary. If you have any questions, please email your instructor. That's the end of Chapter 3 as well, and so we'll wrap it up there. Thanks. Bye.